Welcome to the Bodhi Academy. My name is Abhishek Lasso, and in today's video we'll learn about class 12 chapter 3 chemical kinetics. So previously in this chapter we learned about a first order reaction, and we also learned about a half reaction of a zero order reaction and a first order reaction. Now in today we are talking about the temperature dependence of the rate of a reaction. So here we are going to discuss how basically the temperature increase or decrease in the temperature affects the rate of a reactions. So now we already know that most of the chemicals, they are chemical reactions, they are temperature dependent. Now one example if we have to take about, we can talk about decomposition of N2O5. Now if we see the time taken for the reactant to get converted into the product, like the half concentration of it is determined as follows. So it takes 12 minutes if the temperature is 50 degrees Celsius. It takes 5 hours if the temperature is 25 degrees Celsius, and it takes 10 days if the temperature is 0 degree Celsius. Now we also know that the mixture of potassium permanganate, okay, same example if we talk about with reference to temperature dependence, mixture of potassium permanganate and oxalic acid, now this potassium permanganate which is there, it gets decolorized faster at a very high temperature as compared to lower temperature. Now it has been found that for any chemical reaction, okay, if the temperature is raised by 10 degree, then the rate of the rate constant is nearly double. Rate constant is the value K. So that is it, they are saying it will get doubled. So now the temperature dependence of a rate of a chemical reaction can be accurately explained by the Arrhenius equation. This was first proposed by Dutch chemist known as J.H. Went Hoff, but a Swedish chemist later gave its physical justification and interpretation. So now the equation is K equals to A minus EA upon RT. Now this A, it is known either as the Arrhenius factor, it is also known as the frequency factor, and it is also known as a pre-exponential factor. So it is a constant specific to particular reaction. R is the gas constant and EA here is the activation energy that is given in joules per mole. Now to understand this, let's take a simple reaction of H2 plus I2 giving us 2HI, that is hydrogen, plus iodine giving us hydrogen iodide. Now what Arrhenius says is this regarding this reaction. For this reaction to occur, there has to be an intermediate that has to be formed. Now this intermediate has to be highly unstable so that it proceeds forward in reaction, okay. So this intermediate which is formed, it should last for only maybe a very short time, and then it will break up to form hydrogen iodide. So if we say the energy that is required to form this intermediate, it is called as the activated complex, and it is also known, and this is also known as the activation energy. So in simple words, if you want to say what is activation energy, it is that minimum energy that is required for a reaction or for a chemical reaction to occur. So what happens here, only if this intermediate is formed, only then the reaction will occur further. If not, then the reaction will stop. So therefore we need some limited amount of energy to reach up till this intermediate, and then the reaction continues. So some energy that is released when the complex decomposes to form products. So the final enthalpy of the reaction, it depends on the nature of the reactants and the products. Now all the molecules in the reacting species, they do not have the same kinetic energy. All of them are going to have different kinetic energy, different behavior, as well as different properties. So since it is difficult now for us to predict the behavior of any one molecule with precision, Ludwig Boltzmann and James Clerk Maxwell used statistics to predict the behavior of large number of molecules. So now if we are having n number of molecules, in that case how are we going to predict what is the contribution of each of the molecule? So in that case, these two scientists, they used up the method of statistic to define which molecule is contributing how much. So according to them, the distribution of kinetic energy may be described by plotting the fraction of molecules, that is Ne upon Nt, with a given kinetic energy, that is E versus the kinetic energy. Here now if you look at Ne, it is the number of moles with the energy E, and Nt, it is the total number of molecules that are present. So if we take out a fraction of both these things, we can correlate it with the kinetic energy of all the molecules that are present. Now if we look at this graph, the peak of the curve corresponds to the most probable kinetic energy. So here this peak point, this gives us the probability of the maximum kinetic energy, that is the kinetic energy of maximum fraction of molecules. There are decreasing numbers of molecules with energies higher or lower than this value. Now when the temperature is raised, the maximum of the curve moves towards the higher energy. So if you see, this was the initial temperature, it is T, and then we have increased the temperature to T plus 10. Now here what you see is that the height of the graph is reduced, but you see that the maximum point has shifted its energy level. So initially if we draw a line here to see the corresponding, if the kinetic energy was this much, now if you see the peak is somewhere around here. So if we look, in that case the kinetic energy has now moved and increased, and the curve, it has broadened out, that is spread of the to the right, such that there is a greater proportion of molecules with much higher energy. Now the area that is there under this curve, it must remain constant, since the total probability must be 1 at all times. So we can mark the position of EA on the Boltzmann activation curve as this one over here. This line that is given here, it tells us about the energy of activation. Now increasing the temperature of the substance increases the fraction of molecules which collide with energies that are greater than the activation energy. Now it is clear from the diagram that in the curve at temperature T plus 10, the area showing the fraction of molecules having energy equal to or greater than the activation energy, it gets doubled, leading to the rate of a reaction. So in the Arrhenius equation, the factor that is there, exponential factor E minus EA upon RT, that corresponds to this fraction of molecules that have a kinetic energy that is greater than the activation energy. Now if we take out natural logarithm of both sides of this equation, we get ln of k equals to minus EA upon RT plus ln A. Now the plot of ln k versus 1 upon t, it gives us a straight line graph with a slope of minus EA upon R and intercept of ln A. Thus, it has been found that from Arrhenius equation, the increasing temperature or decreasing activation energy, it will always result in an increase in the rate of the reaction and an exponential increase in the rate constant. Exponential as in slow increase will be seen. So now if we have at temperature T1 the same equation, if we take ln K1 equals to minus EA upon RT1 plus ln A. So at temperature T2 we will have a similar equation. Now since A is a constant for a given reaction, K1 and K2 are the values of rate constant that corresponds to the temperature T1 and T2. Now if we subtract the equation 3.20 from 3.21, we can obtain that ln K2 minus ln K1 is equals to EA upon RT1 minus EA upon RT2. Now if we separate out this 1 upon T1 minus 1 upon T2, we can write it outside a bracket. So EA upon R, we are basically taking this part common and writing the rest of it. So now removing this natural logarithm, we can add log, and we have EA upon 2.303 R 1 upon T1 minus 1 upon T2. On rearranging, now if we cross multiply this, we will have T2 minus T1, that will be delta T upon T1 into T2. So that tells us about the temperature dependence of any reaction with reference to rate constant. Okay, so that was it for today's video. I hope you have understood. Please don't forget to like, share and subscribe to the Bodhi Academy.